Here's the next example. 28.2. A 0.1 kilogram ball is dropped from a height of 5 meters. It hits the floor and rebounds to a height of 4 meters. A. What's the ball's vertical velocity just before it strikes the floor? B. With what vertical velocity does it rebound? C. How much energy does it lose during the contact with the floor? The diagram here shows the ball actually following a curved path. It doesn't matter whether it follows a curved path or whether it follows a straight path. The kind of forces that are at work during the time that it's in the air is the weight force, which is path independent. During the time that it's in contact with the ground, there are non-conservative forces at work. And it turns out that there are some conversion of energy into thermal energy as the ball rebounds. We're going to deal with that part in part C. Let's start with part A. The energy the ball has when it's at the top at 5 meters is going to be gravitational potential. It's being dropped, so it has no kinetic energy. Right before it comes in contact with the floor, before the floor begins to exert non-conservative forces on it, the energy it has at the bottom is completely kinetic. And so I can apply conservation of energy to figure out how fast the ball's going right before it strikes the floor. At the top, its kinetic energy disappears. At the bottom, its gravitational potential energy disappears. Let me write the formulas for the gravitational and the kinetic energies at the top and the bottom. I'm going to use the subscript T for top and B for bottom. Again, the masses disappear, and I can solve this for the speed at the bottom. Put in the numbers, then put it in my calculator. In part A, I find that when the ball gets to the bottom of the first part of its path, it's moving at a speed of 10 meters per second. Now what about part B? In part B, I'm going to look at what happens to the ball at the instant right after it leaves the floor, and then it rises to a height of 4 meters. And I can apply conservation of energy again, saying the energy that the ball has at the bottom, now this is after its contact with the floor, this is after, right at the instant it loses contact with the floor, all of its energy is kinetic. It rises to 4 meters. It comes to a stop. So for an instant in time, its energy is gravitational potential. Let me write that down. Conservation of energy. And again, the kinds of energy we're dealing with here are kinetic energy and gravitational potential. And some things disappear. So I can say 1/2 mv bottom squared is equal to mgy top. Again, this is the second half where the object goes up to 4 meters. Again, the mass disappears, and I can solve that equation for how fast the ball must have been going at the bottom in order for it to rise to 4 meters. And I'll put in the numbers and put it in my calculator. And I get that the object must have left the floor with a speed of about 8.94 meters per second. Now, where did that energy go? I had a kinetic energy that gave me a speed of 10 meters per second right before the object hit the floor. Now, there's work that's done as the object is in touch with the floor, and now the object leaves the floor with a speed of 8.94 meters per second. That energy went into other forms. Kinetic energy was converted into other forms. Heat, sound, there may have been some wind that was generated. The idea is, though, I don't have as much kinetic energy in the ball after it makes contact with the floor, after the floor does non-conservative work on it. Again, while it's in contact with the floor, there's no change in elevation, so we're going to say that there's no gravitational potential energy changes. All the energy changes are kinetic energy while it's in contact with the floor. Now, the final kinetic energy is the kinetic energy it has when it leaves the floor to go up to 4 meters. The initial kinetic energy it has is going to be associated with how fast it was going right before it came in contact with the floor. So I'm going to put those numbers in. And here, this kinetic energy does depend on how much the ball's mass is. The mass doesn't cancel out in this one. And now I feed it into my calculator. I get that the ball loses 1 joule of energy while it's in contact with the floor. Somewhere that energy was given up in the form of heat, in sound, in other dissipative forces. The idea is that there's 1 less joule available to the ball in kinetic energy when it leaves the floor. Now let's go to our last example. A 3 kilogram ball is dropped from rest and falls a vertical distance d equals 55 centimeters. We're going to convert that to meters. Before striking a spring oriented vertically as shown. The spring as a result of the impact compresses x equals 15 centimeters. Again, we'll convert that to meters. What is the spring constant of the spring? Now, notice that I don't just have the spring in equilibrium here. The spring is going to be compressed, and then the spring is going to rebound. It's not just the ball is going to be sitting on the spring here. The ball actually has some motion before it actually compresses the spring, and I've got to account for that. So I can't just apply Hooke's law here and say, oh, well, the ball compresses the spring by 0.15 meters and the ball has a weight of 3 kilograms. Let me set those forces equal to each other. No, the ball has some kinetic energy when it strikes the spring. And so I can't just apply Hooke's law here because the spring is not in equilibrium. The ball is not in equilibrium when it gets to its lowest point. Now, you may have noticed that from the diagram in the textbook, I have omitted part of the diagram to figure out what's going on. I want to look at the types of energies that are involved in this situation. There are 3 kinds. I have gravitational potential energy. I have kinetic energy, the ball's in motion. And I have elastic potential energy. There are no other forces that are at work. We're disregarding non-conservative forces in this. And so I can talk about the total energy of the system at any point and say that the total energy at the beginning, the total energy at the end, the total energy in the middle is all going to be conserved. Now this can be kind of disconcerting. How do I deal with this? How do I deal with all 3 energies at one time? It can actually be liberating in terms of being able to find out things about the motion of the system, and we'll see how to use that liberation in future lessons. But for right now, it might seem a bit bewildering. Are there some strategic places where only one type or the other is involved? And I would suggest yes, there are some strategic places. There are 2 of them. One is at the very top and the other is at the very bottom. Since the ball is dropped from rest, there's no kinetic energy involved, and the spring's at its natural length. So at the very top, the only game in town is going to be gravitational potential energy. At the very bottom, when the spring compresses to its maximum amount, right before the ball rebounds, there's going to be an instant at which the ball stops moving downward and starts moving upward. And at that instant, and it's only for an instant in time, the ball is not moving. So there's no kinetic energy. And if I think about the very bottom, the very lowest point down here, and set that as my y equals 0 level, I can say there's no gravitational potential energy. So that the only game in town there is elastic potential energy. Now, what are we trying to find? We're trying to find the spring constant. I could say that conservation of energy will tell me that the gravitational potential energy that the object has at the very top, and when I say gravitational potential energy, I mean with respect to where the maximum compression of the spring is, that the gravitational potential energy that it has with respect to that level is going to be equal to the elastic potential energy that there is at the bottom. And I'm going to solve the problem that way. So here is my statement of conservation of energy, and now I'm going to cut to the chase. I mean, I could say the kinetic energy at the top plus the gravitational potential energy at the top plus the spring energy at the top is equal to the kinetic energy at the bottom plus the gravitational potential energy at the bottom plus the spring potential energy at the bottom. But I only have gravitational potential energy at the top and spring potential energy at the bottom. Now, how high from the very bottom is the ball when it's at the very top? What I claim is that y at the top is going to be equal to this distance, 0.55 meters, plus the amount that the spring compresses, 0.15 meters. And now I've got it. I know what the mass is. I know what g is. I know what y at the top is. I know what x is. Solve that equation for the spring constant. Here we go. And now let's feed in the numbers. And I get that the spring constant is not quite 1900 newtons per meter. I will let you work out the units to see that in fact it is newtons per meter. That is an application in which I apply conservation of energy. That's it.